Magnets, omnipresent yet frequently overlooked, wield their unseen forces in myriad ways throughout our daily lives. Delving into the fascinating realm of magnetism unveils a captivating narrative that extends beyond the familiar realm of refrigerator adornments. Surprisingly, almost all known materials exhibit some degree of magnetic influence, although often imperceptible to the naked eye. In contrast, certain materials possess a more pronounced magnetic force, earning them the distinction of magnets. These magnetic marvels not only find themselves adorning fridge doors, but also play pivotal roles in diverse applications, ranging from powering advanced medical devices such as magnetic resonance imaging, MRI, machines, to contributing to electricity generation. Let's see how they make them in factories from raw material and how many different magnets there are. Additionally, permanent magnets can be artificially created by exposing specific materials to a magnetic force. Understanding the nuances of magnets requires a closer look at their various types. Firstly, there are permanent magnets, exemplified by the natural magnetite, commonly known as lodestone. These magnets exert a consistent magnetic force without external intervention. The key characteristic is that these materials retain their magnetic properties even after the external force is removed. On the other hand, electromagnets are generated by surrounding certain materials with a coil of wire. When an electric current flows through the coil, these materials exhibit a magnetic force. However, once the electric current ceases, the magnetic effect diminishes significantly. Now, let's demystify some of the terminologies used. Coercivity refers to the ability of a material to resist demagnetization. In simpler terms, it measures how resistant a magnet is to losing its magnetic properties. Higher coercivity implies greater stability of the magnet's magnetic field over time. Remanence is another crucial term, denoting the residual magnetic induction retained by a magnet after the removal of an external magnetic field. Essentially, it reflects the magnet's ability to remember its magnetic state even when the inducing force is no longer present. The intricate process of magnet creation involves various materials and meticulous steps. Consider alnicomagnets, composed of aluminum, nickel, cobalt, and additional elements like copper, iron, and titanium. The proportions of these elements are meticulously controlled, as they directly influence the resulting alloy's magnetic properties. The initial stage involves casting the raw metals into molds, typically crafted from heat-resistant materials like sand. This meticulous molding process ensures the formation of magnet shapes that serve as the foundational building blocks for subsequent manufacturing steps. The casting process itself is a pivotal determinant of the magnet's final structure and composition. Following casting, the magnets undergo a controlled cooling and solidification phase. This step is critical for establishing the microstructure of the alloy, which in turn influences its magnetic characteristics. Once cooled, the magnet shapes are subjected to magnetization, a process aligning their magnetic domains and imparting permanent magnetization. This crucial step involves utilizing electromagnetic coils, often shaped as solenoids, to generate the necessary magnetic fields. Enter heat treatment, a pivotal stage in the manufacturing process designed to optimize the magnetic properties of the alloy. Heat treatment enhances coercivity and remanence, creating a magnet with stable and reliable magnetic behavior. The subsequent magnetization process is where the magnet truly acquires its magnetic properties. Despite previous exposure to a magnetic force, this step aligns the magnetic domains within the alloy, imparting permanent magnetization to the material. Following magnetization, magnets may undergo machining and grinding processes to ensure they meet specific industry and client requirements. Quality control checks become paramount at this juncture, encompassing thorough magnetic property analysis, dimensional inspections, and visual assessments. These checks are instrumental in guaranteeing compliance with industry specifications and ensuring the magnets meet the highest standards. The relentless pursuit of innovation propels ongoing research, aiming to discover even more potent magnets. In the 21st century, powerful electromagnets are harnessed for revolutionary applications like maglev trains, where magnets enable these trains to float above guideways, minimizing friction and allowing remarkable speeds exceeding 310 miles per hour. This captivating journey into the world of magnets invites us to ponder the endless possibilities that lie ahead, inspiring curiosity and appreciation for these remarkable forces that quietly shape our modern world. As we marvel at the current applications of magnets, the future holds the promise of unforeseen possibilities, driven by the relentless pursuit of knowledge and innovation. Magnets, with their inherent mystique, remain at the forefront of transformative technologies, showcasing their potential to reshape our technological landscape in ways we are only beginning to comprehend. The history of magnets goes back to ancient times when people discovered magnetite, a natural iron ore with the ability to attract iron objects. The Chinese developed the first compass using magnets for navigation. In the 16th century, William Gilbert's work laid the foundation for understanding magnetism as a force. Scientific exploration in the 18th and 19th centuries linked electricity and magnetism. Advances in metallurgy led to the development of powerful magnetic materials in the 20th century. Today, magnets are essential in various technologies like electric motors, MRI machines, and more, showcasing a fascinating journey of discovery and innovation over the centuries. If you found this video interesting, subscribe and like this video for more. Thanks for watching.